Hello everyone. I'm very pleased to be here today to speak with you about this structure preserving method. And so, okay, let's begin. I'm going to talk about a certain method to preserve the structure while discretizing in space a certain system, which is the Cahn Hilliard equation, which I will present to you, in a certain framework, which is the port Hamiltonian system, which I will also present to you very briefly. Okay. So first of all, some motivation. Let's say you have some water, like this just here, which is salty water, and you want to drink it, but you have an issue, which is it is very salty, so you want to remove it. There is a lot of different methods to remove the salt from water, but one of them is to basically freeze it, because by freezing it, you make some crystals, which will float at the top, and the salt will be sinking in the bottom, and you get your clear water at the top. Okay, and we want to describe the system for control problems, and so you need at least a couple models. You need one for convection, of course. You need one for the heat equation. You need one for the phase transition. And finally, you need one for the salt concentration. And this Cahn Hilliard model will allow us to describe how the salt and the water goes from one to each other. Okay. So I will present to you the continuous model. So the Cahn Hilliard model. We have a so-called phase variable, which is by convention between 0 and 1. And we are going to say that, for instance, when phi is equal to 0, we have like pure water. And when phi is equal to 1, we have salt which is saturated in water, for instance. It can also be used when you have, for instance, water and oil, and you have phase separation between the two. And so phi equal to 1 will be oil, and phi equal to 0 will be water. But because it's a phase field variable, you have this kind of continuous transition between phi equal 1 and phi equal 0. And so this is penalized by this term here, which allows us to minimize the interface in our system. Okay. Finally, G will be our bulk free energy associated to our phase. And it will have a double well potential form, which allows us to say that water is a stable phase, oil is a stable phase, but between the two it's not so stable, and it forces our system to choose between either water or oil. And finally, we have this equation, which shows that the phase is conserved because we have, for instance, when water and oil evolve, we have still the same amount of both in our system. And the flux is a gradient of the functional, which allows us to make it decreasing over time. Okay. So now, what about port Hamiltonian systems? They are made of mainly three spaces. The first one will be our state space, which is basically the state of the system. And the two others will dictate our dynamics of our system. We have the effort and flow space. Okay. In classical Hamiltonian mechanics, the flow space can be thought as the generalized moments and position, and the effort space can be thought as the generalized velocities and forces. To link these three spaces together, we have two structures. We have the Dirac structures and Lagrange structures. The first one will allow us to have some kind of energy routing between the different elements, and the second will allow us to get some kind of Hamiltonian, an energy basically. And so we have this diagram, which allows us to visualize how things are interconnected. Okay. And finally, we have some kind of state space representation, which allows us to do simulation and controls, which is given as this. You have to be careful because J is antisymmetric and R is symmetric, semi-definite positive, which allows us to get this power balance equation, which shows that by construction, our system is passive. And here we have some dissipation. Okay. So we have port Hamiltonian systems, and we have our Cahn Hilliard model. So now let's rewrite the Cahn Hilliard model in the port Hamiltonian framework. To do so, we are going to extend our state space by considering the gradient of phi as an added variable. This allows us to remove the operator from the Hamiltonian and allows us to get an explicit Lagrange structure instead of an implicit one that we would have had if we were to keep the operator in the energy. Okay, we can then rewrite our system as this. Okay, and there you can see that this operator is formally antisymmetric up to boundary terms, because here we can see that div and grad are, the adjoint of div will be minus grad, so this is antisymmetric, and this are both symmetric operators, so this is indeed antisymmetric. And you have this resistive relation, which allows us to get the following free energy balance, which shows that our free energy is decreasing because gamma is positive, this term will be always non-positive. And these are the boundary controls of our system. You can see that all these boundary controls and observation are always co-located. For instance, here we have the flux at the boundary co-located with its co-energy variable. So in this Hamiltonian framework, you always have the control and observation co-located, which allows you to get passivity of your system. Okay, so now we have our Hamiltonian system, and we want to do structure-preserving discretization. So we want to get from a continuous Dirac and Lagrange structure to a discrete one. Okay, to do so, we are going to use finite element method, which will go in three main parts. The first one is basically to write the variational formulation of the system, then to integrate by parts our system, to exhibit the controls and exhibit the skew symmetric property of our structure matrix, and finally choose a set of finite element families to do the simulations. Okay. An important part is that the finite element families and the integration by parts are not independent. Okay? Because for instance, the grad div is a second order operator. So if you integrate by part one time this operator, you get some kind of div time div in your matrices, which allows you to use h div finite elements. Whereas if you keep it this way, it's second order, so you have to use h2 finite elements. Okay. So now we do this on the second line as an example. So we take the second line, which is with the psi here. We write the variational formulation of our system, then integration by parts. And there you can see that we have the div, as I said before. And here you get your boundary control. Okay? And then you can define, so this is the definition of our discrete variable. So we put a bar over our variable to talk about the coefficient. And then we can define our different matrices. So we have three kinds of matrices. We have the structure matrices, which are not square, which are rectangular matrices. Then we have our mass matrices, and finally the constitutive relations matrices, which are basically mass matrices with some kind of weight added to it. Okay. Once we've done that, the second line can be discretized as this. And so you can see we have, this is the dynamics, this is our control, and this is our discretized constitutive relation. And so when you do that on the whole system, you get this, which is our complete system with here an antisymmetric matrix, here the control, and here the collocated observation. Okay? And here a constitutive relation. One important remark is that this constitutive relation here is non-linear, so that means that numerically you have to compute this at each time step, and you also it's preferably better to use explicit time integrator for this line because it will work better. Otherwise you get some error with your solver which does not necessarily converge. So in our setting we use an explicit time integrator for this part of the system. Okay. Then, okay, so now I'm going to show you that we preserve some properties, so it's structure preserving. So first of all, the free energy balance is kept consistent. So if you define the free energy as basically the same free energy, but with a discretized variable, you get the same energy balance, okay? So this part here corresponds to this part here, and this is the control part of our system, which is this part here discretized. A second important point is that the discrete phase is a conserved quantity. So if we recall, the discrete phase was something equal to minus divergent of a flux, so it's a conserved quantity. And at the discrete setting, you keep this exact same property with a discrete counterpart. And numerically, when you compute this, you get to machine precision, which is rather nice. Okay, so we've taken our continuous system, wrote it in the pH framework, we have discretized it, and now I'm going to show you some results. So first of all, some images. So we take, for instance, at the beginning, some kind of random initial condition, and then we integrate by with respect to time, and in the end, you see that you have phase separation, and as you can see, it tends to also minimize the surface area at the boundaries. I'm also going to show you a small video. So here, yeah, nice. Yeah, let's see. Okay. So, okay. So on the left side of the screen, you will see the phase, okay, which we initialize with some kind of function, and on the right, which is not very clearly visible, you have the gradient of the system. So just focus on the phase on the left, and you'll see that it will differentiate between 1 and 0 and the clump together, basically. Okay. So we start the simulation, and you see that the phase tends to separate between 1 and 0 and minimize the surface at the interconnection. Here. Okay. Okay, so in conclusion, we have successfully applied the structure-preserving discretization method to our Cahn Hilliard system, and the outlook is basically to use this system and couple it to the other one that I talked about to simulate the whole freezing process of the salty water, and this would be a great goal. And finally, here are some references. And here, the work we already did on the Allen-Cahn heat equation, which are the other equation I talked about. Okay, so do you have any question?
Thank you very much. Is there any question or comments? Please.
So this was a finite element discretization.
Yep.
Right? So what water basis function?
We use P1. Basically, yeah.
And the mass, did you do some kind of mass lumping?
No, we kept the mass matrix intact, yeah.
Is there any question or comment? So in discretization, so you mentioned that fully discretized, but I guess it's semi-discretized.
Yeah, only in space, sorry, yeah, only in space.
So
yeah.
what kind of structure is preserved?
Oh, okay. What we preserve is the Lagrange and Dirac structure, I would say, and for the time integration, it's still an open problem to properly discretize a Hamiltonian system in space. So we use the implicit midpoint rule, if that's your question. But in the semi-discretized case, where you only discretize the space variable, there the Dirac and Lagrange structure are discretized. Yeah.
So, but finally, you need to discretize in the time
yeah.
direction.
Yeah.
So then your fully discretized structures also Dirac, discrete Dirac.
Okay. So that's a very interesting question actually, because so for now you can define discrete and continuous Hamiltonian system with continuous time in both cases, but defining a discrete pH system with discrete time is difficult because you don't have uniqueness, and it's difficult to say which one is the best. But if you want to do it, you can, for instance, use the midpoint rule, which will get you in the linear case preservation of energy and so on, and so you get some kind of structure preserving. But the issue is that defining structure preserving necessitates that you have a structure to at the discrete level, which is not yet clearly defined. So.
So one more can I ask? So I'm just wondering, what is a Lagrangian structure in a sense?
Lagrange structure. Okay. So okay, I'm going to go back. Here, okay. So the Lagrange structure, so in the easy case, it's basically just that you have a Hamiltonian, and the effort are the gradient of the Hamiltonian with respect to the state space. But in a more general setting, you can, okay, so in the linear setting, you can just say that it's a symmetric relation between your effort and space variable, okay? And in the general case, if I remember well, it's saying that locally you can find a Hamiltonian. And you have to, yes, you have to satisfy some kind of symmetric relation, which I can talk to you about later. Okay, so that's a good question. So in this model, it's free energy, but in general, you can just take any thermodynamics functional. So you can do with energy, with entropy, and with whatever you want. But an interesting open problem, which is still yet to be resolved, is how do you use, like, for instance, the energy as your Hamiltonian, but then still want to have irreversible processes occurring, because then you also need kind of your entropy. And so, so in general, it will be like the energy routing or the entropy routing and so on and so on. It's just energy routing in this case, but it can be entropy routing.
Still we have some time, but okay, please.
You met the operator presents resistive effects in your problem. Do you use it? Which is the physical?
Okay, so this operator is a.
You have only J.
Oh yeah. Okay. Nice question. Okay. Yeah. So yeah, indeed. Okay. Because the flow and effort variable, so F and E, can also allow you to put apart the resistive part of your system, and so indeed J is antisymmetric, but as you can see in F phi and J phi, you don't have any time derivative. And so this flow and effort variable will correspond to your resistive part of the system. And basically what J is saying in this setting is that energy is being put into the resistive part and dissipated. And so you can write it either with the R matrix or R operator, which is symmetric, for instance, or like this, with putting outside of the R matrix the resistive relation. And so you.
There is a resistive effect, but it's a variant of the
Yeah, it's basically it's writing the thing before with putting outside the resistive relation, and so your R matrix is the gamma here at the bottom. Yeah, the R matrix would correspond to this operator in a way, and we're just like putting it outside of the structure. Yeah, I don't know if that's very clear, but.